A very good morning, my dear students. In this session, we are going to finish the chapter called Electromagnetic Induction. Alright, now let's see the topic called Growth and Decay of the Current in LR Circuit. Growth of the current we have discussed already when a circuit in which an inductor is involved. The decay of the current is also we had discussed, that's called the basic concept of inertia of electricity. What this inductor will do in this circuit, it will opposes the change of the current. Okay, now so before going into this topic, I would like to tell you what is I naught. I naught is the maximum value of the current. What is this I naught here? So the maximum value of the current in this circuit, I have considered it as I naught, right? So this is the maximum value is equal to E. What is the voltage applied to the circuit by resistance of it? This is R, right? Resistance of it. Now, this is the tau. This is also most important thing. This tau is called a time constant. What is this? Time constant. If you write the dimensions of the inductance and dimensions of the resistance and you get the dimensions of the time, what you get? The dimensions of time. Okay. Now that's why it is called as a time constant. What is this time constant? The ratio of your L value and R value. That's called the time constant. And what is the importance of this time constant? You'll understand it now, right now, right? Let's begin the concept. This is a circuit where a battery of voltage E is kept here, whose positive terminal and negative terminal have mentioned in this way. And in this circuit, there is a resistance and inductor. Both are connected in series combination. Now there is a switch. So here S is the switch here. A and B are 2 points. First, what I am doing here, the switch is connected to A. Switch is connected to point A. What happens? Imagine the switch is connected to point A. Positive terminal and the current will start flowing through this circuit. Yes or no? Current will start flowing through this circuit. Initially, the current value is 0. Understand? Initially, current value is 0 and the current value will slowly rises and reaches to the maximum. But to go to the maximum value, to reach the maximum value, it has to overcome some opposition. What is that opposition? That opposition is by the inductor, because it will delay the growth of the current. It will delay the growth of the current. Alright. So that's called the change of current. It will oppose. Okay. Now, when the switch is connected to A, what is the situation takes place here? A growth of current. The first case, let's say the growth of the current we are talking about. Growth of the current from where to where? From I is equal to 0 to I is equal to I naught, right? From here to here, the growth of the current takes place, my dear children. Now, from the Kirchhoff's laws, let's apply, right? From the Kirchhoff's laws, let's apply the Kirchhoff's voltage law here in this circuit, right? In this circuit, it's my loop. So this is the inductor will have an induced EMF as the growth of the current is taking place, and the induced EMF direction, the cell direction is like this. Let's apply Kirchhoff's voltage law. Here, imagine the current I is flowing at this instant. Okay, so this is minus I into R. This is our current direction is touching the positive terminal. That's why it is minus E. And we are moving in this direction, and our current direction is striking the negative terminal of E, capital E. So that's why I can write plus E, which is equal to 0. From here, so what I can write, E is equal to IR plus E, and this I can also write IR plus, so this E is L into di by dt, right? So what is this? What is this? So I can write it E is equal to IR plus L into di by dt. If I differentiate this expression, my dear students, if I differentiate that expression, the most important thing we are going to discuss. If I differentiate this expression, I get it from where to where? From the limits I to I naught. Look at here. From the limits I to I naught, if I differentiate, the differentiation I am not doing right now because that is not at all required for your exams even. Okay. So if I differentiate the solution of this differential equation, you get it in this way. I is equal to I naught into 1 minus e to the power minus t by tau. Look at here. So t is the time. So small t is the time at a particular instant. The time at a particular instant, and whereas tau is the time constant which is equal to L by R. Alright, which is equal to L by R. Now, if you carefully understand the situation here, this is the solution of this differential equation. Right? This is the solution. Here, let us substitute the time. For example, when time is equal to 0. When time is equal to 0. What is that? I is equal to I naught into 1 minus e to the power minus 0 by tau. E to the power minus 0 by tau. Minus 0 plus 0, everything is same. So it is like e to the power 0. E to the power 0 is what? E to the power 0, I can write it as 1. So 1 minus 1 is 0. 0 into I naught is 0. So when t is 0, I is 0. That's what we discussed. When time is 0, so what happened? There is no current. Understand? So now when time is infinite, I is equal to I naught into 1 minus, carefully see, it is e to the power minus infinity. Understand? When t is infinity, infinity by something is infinity. Understand? Infinite by infinite is something. Infinite by infinity is, infinite by something is infinite. E to the power infinite will be, see, I'm writing here, e to the power minus infinite, I can write 1 by e to the power infinite. E to the power infinite is infinite. 1 by infinite is 0. Okay, clear? So what I can write here, so e to the power minus infinite you will get, so that is 1 by e to the power infinite, 1 by infinite is 0. 1 minus 0 is 0. I naught into 1 minus 0, it is I naught. Okay. And the most important part, I'll tell you, my dear students, the most important part comes here. So when t is equal to tau, what is that? When t is equal to tau, which is equal to L by R, carefully see. So I is equal to, from here, I is equal to I naught into 1 minus e to the power, carefully see, e to the power minus tau by tau. T is tau, right? This is time constant. Minus tau by tau, it's minus 1. Okay, e to the power minus 1. So this will be, carefully see. So generally, the E value will be 2.718. E value, exponential value, 2.718. So here 1 minus 1 by 2.718. Okay, so this I can write it as 0.63 times of I naught. Carefully see. This is the very important point here. So from this, I can represent in the graph the same, the complete thing I can represent in the graph, and these are the values of current and these are the values of time. 0. When time is 0, current is also 0, starting from here. When time is infinity, current is reaching to maximum value. Current is reaching to maximum value. This is I naught, right? Look at here. So current is reaching to the maximum value at infinite, right? It goes like that. Now, at t is equal to tau, for example, at this particular point, imagine t is equal to tau, which is equal to L by R. So what happens here? T is equal to tau. See here. So this is the point you imagine. It's a 0.63 of I naught. At what time the current value is 0.63 times of I naught, that's time is called time constant. The time is called what? Time constant. That's what I wrote in these brackets. Look at here. Inductive time constant of a circuit is defined as the time in which the current rises from 0 to 63% of its final value. What's the final value of the current? It's I naught. 63% of the final value is 0.63 times of I naught. That's it. So at which time it is happening, that's called inductive time constant. Alright. Clear? The only thing you should remember is this formula, and 99.9% you will not be asked this question in the final NEET exam. Based on this, you will not be asked any question. But if you are writing, if anybody is writing JEE exam, and this is the concept is important for them. Okay, so this is the concept is important for the JEE students. For CET and NEET, there won't be any question from this, but try to remember the value. Sometimes the 1% chance is there, so that 1% is also trying to remember these values, right? In case of growth of current, what happens at the time constant? At time constant, which is equal to L by R, exactly the current value will be 0.63 times of I naught. It's so simple. Now, let's look at the decay of the current. Let's look at the concept of decay of the current. It's so simple, my dear students. So decay of the current, now what I'm going to do here is, now my switch I've connected to B, right? When the switch is connected to B, what happens here? Positive terminal of the battery is connected to one end and the negative terminal is not connected to anywhere. So that means no current flows, right? No current flows from external source. I'm telling you here, no current flows from external source. But already the current value is reached to the maximum in the circuit. So from where this current goes now? Understand? So here the important thing, the decay of the current takes place. What is that? The decay of the current takes place in this case, and that decay will be from I naught to 0. That's important. Maximum value current has reached in the time infinity. Okay, it is reached to the maximum value. Now the decay takes place from maximum value to the 0. Alright? Clear? Now, here also if you apply Kirchhoff's rule and you will get a differential equation, and the solution of this equation here, you get it as I is equal to, carefully see, I is equal to I naught into e to the power minus t by tau. It's so simple. I is equal to I naught into e to the power minus t by tau. So here let's write, when time is equal to 0, I is equal to I naught into e to the power minus 0 by tau. It's a 0, so which is I naught. E to the power 0 is 1. Anything to the power 0 is 1. So at initial time, at time is 0, what is the value of current? It's maximum. Okay, so let me draw with graph also here. These are the time values and this is the current values. So this is the maximum value of the current. Imagine this is I naught. At time is equal to 0. See, current value is maximum. Then the decay takes place. Now, imagine when time is infinite, what happens? I is equal to I naught into e to the power, again see, e to the power minus infinite by tau. Infinite by tau is infinity. So minus infinity. E to the power minus infinity will be 1 by e to the power infinity. E to the power infinity is infinity. 1 by infinity is 0. So that's what I can write here. So this is 0. At infinity, so value of the current reaches to 0. So minimum value, we get it like this, it goes. Right? It goes. Here also it is going like this, you can see. Here also. Understand? At infinity only, the minimum value of the current it reaches. Now, at t is equal to tau, which is equal to L by R, what happens? I is equal to I naught into e to the power minus 1. It's I naught by E. And you know the E value. What is the E value? 2.718. So I naught into 1 by 2.718 and it will be, so it's very simple that you get 0.37 of I naught, my dear students. This is the this is the value, we call it as, at this particular value, that may be here, you can see that may be here. So this is 0.37 of I naught. At what time it is happened? When t is equal to tau, which is equal to L by R, it is happening. So this is called this one. Inductive time constant can also be defined as the time interval during which the current decays to 37% of the maximum current, right? So 37% of the maximum current. So current at this particular instant will be 0.37 times of I naught. Look at this expression. Clear? So this is how we discuss delay of the current and the growth of the current in LR circuit, right? I hope it is very much understandable for you, and the numericals will be asked in so simple ways. They will give E value and R value. They will ask you to find I naught. I naught is the maximum current. In one way, this kind of questions. In the other way, they will give you the L value and the R value. The ratio of this is called a time constant. It's so simple. Okay. The numericals will be asked based on this. That's it. Alright. So, in detail, the concept we have discussed, and there's no much discussion is required other than this. Right? So, look at the two important graphs. Here, when time is infinity, the current is reaching to maximum. Here, when time is infinity, the current is reaching to minimum. Actually, the current needs to decay to the zero value immediately. But because of this inductor, there is a delay is taking place. Here also, current immediately to reach the maximum value. But because of the inductor, so there is a delay is taking place in the growth. Right? That's the work of the inductor. Inductor will opposes the change of current and resistor just opposes the flow of current. That's it. Okay. And let's discuss about AC generator in detail now. The last topic of this chapter and this session is AC generator. What is this AC generator? In the last class I had given you a simple introduction about AC generator. Here AC stands for alternating current. Generator generates electricity from mechanical energy to electrical energy. It generates mechanical energy to electrical energy. That means it converts mechanical energy into electrical energy. Alright? Now, so the first scientist designed the device AC generator is Nikola Tesla, and the modern AC generator gives an output of 100 megawatt electrical energy. This is about the basics of AC generator. Now let's talk about the principle of AC generator. So simple. Principle of AC generator is electromagnetic induction. That's the name of the chapter even. What is electromagnetic induction? the production of induced EMF due to the magnetic flux change. That's called the EMI, right? So what is EMI here? It is the production of induced EMF due to the magnetic flux change linked with a coil, right? So that's what principle of electromagnetic induction, the principle of AC generator. So let us talk about the device and its construction in simple terms. Device and construction, let us discuss here. There is a north pole of a magnet and a south pole of a magnet is kept here. Okay. Here there is a rectangular coil which is kept here, and this rectangular coil is named as A, B, C, D. If you really understand the situation here, the point A is connected to a longer lead, point D is connected to the shorter lead. Okay. And the shorter lead is connected to a ring called S1. Longer lead is also connected to a ring which is called S2. Okay. Now both the rings are having connections carbon brush 1, and this is permanent connection. Okay, this is carbon brush 2. And there is a galvanometer is kept here. This is the galvanometer is kept. Why? Because our aim is to produce electrical energy from mechanical energy. Whether the electrical energy is produced or not, how you will be checking? So we'll use by using galvanometer. We'll keep the galvanometer in the circuit. If there is a deflection in the galvanometer, so that is 100% confirmed that there is a current produced in that. Understand? Clear? So this is the basic construction. In the basic construction, what all the things are involved, let us check. What are the things are involved here? So this is the bar magnet, and the bar magnet is called horseshoe magnet. What is it called? Horseshoe magnet. And there is an armature coil. So you know what is this armature coil? It's a coil wound or a soft iron core. That's all. Armature coil, and it's A, B, C, D is the armature coil. And there are slip rings. What are those? Slip rings. Slip rings. They are not split rings. Split rings will come in DC motor topic, right? So split rings will come in DC motor. Slip rings will come here AC generator. Wherever there is a concept called alternating current, there are the presence of slip rings, and these are the carbon brushes, right? Carbon brushes and the galvanometer. That's it. And the galvanometer. These are the things present in this construction. Now let's see, this is what an imaginary axis, and we are just, carefully see, we are just rotating this coil in this direction. Look at here, we are rotating the coil in this direction. My dear students, look at here carefully, we are rotating the coil in this direction. Alright, and before moving to that, what is the angle between theta? What is theta value here? Angle between magnetic field and area vector of the coil. So this is the coil whose area vector is in this direction and the magnetic field lines are in this direction. Alright, these are the magnetic field lines. These are the magnetic field lines. Outside the magnet, they move from north to south. What is the angle between magnetic field lines and area vector? Tell me. What's the angle between magnetic field lines and area vector? What is that? It's 90. So theta is 90 degrees. Okay. So this is initially the angle between B and A of the coil. Okay. Keep it aside. Now, here, imagine this point here. This is the point. How this point is moving, and this is the point is moving in this direction. Alright. So this is what the motion of the conductor direction. This is the motion of the conductor like that. At this point you focus. Motion of the conductor is like this, and the magnetic field lines are like this, and you see my middle finger direction upwards. Again I am telling you, by using Fleming's right hand rule. So by using Fleming's right hand rule, okay, Fleming's right hand rule is used to find induced current direction. I hope you could remember this. Fleming's right hand rule is used to find induced current direction. Okay, so now this is what the motion of the conductor, magnetic field lines, and you can see the induced current direction. So induced current direction is like this, like this, like this, like this. See here. At this point, induced current is touching this slip ring here. And an important point is this longer lead is not at all will have connection with this slip ring S1. Right? So imagine if this is the slip ring, so this lead will just pass through it like this. Right? There's no connection. Understand? So in this way, this longer lead will just pass through the slip ring S1 and it will have connection to S2. Okay. So when this coil is rotating, so these rings will be rotating in this way. Without any connection, it will rotate here. Okay. So now current is passing through the shorter lead having connection with S1, slip ring 1. Slip ring 1 is having connection with C1, and the C1 current pass through in this direction through the galvanometer to the C2. C2 is having connection with slip ring S2. S2 like this. Understand? Clear? In this way, current flows through the coil in first half rotation. So in first half rotation, what happens here that you should understand. So your C1, carbon brush 1 behaved as a positive terminal, carbon brush 2 behaves as a negative terminal. Yes or no, my dear students? Tell me. Carbon brush 1 behaves as a positive terminal. That means current is flowing in this direction. Okay? Clear? Now, second half rotation. Imagine this is completely rotated in this way. Alright? So how it is rotated completely, and let me draw again here. This is my north pole and this is the south pole here. This is my ABCD rectangular coil, which is called armature. Right? What happens? Now everything is changed, right? So this comes here. CD comes this part. So this is my CD and this is BA, right? So A is connection with the longer lead. So I'm drawing the same here. A is having connection with the longer lead and D is having connection with the shorter lead. So this is the shorter lead. So shorter lead is connected to S1 and the longer lead is having connection to S2, whatever it may be. S1 is in permanent contact with the carbon brush C1, S2 in permanent contact with carbon brush C2, and there is a wire connected C1 and C2 that is connected with the galvanometer. Alright. Now this is same. the imaginary axis of rotation is same. So magnetic field lines are also same here, north to south outside the magnet. Okay, now this is the second half rotation. Okay, first half, this is the second half rotation. What is going to happen? We are going to check. Let's check what is going to happen, my dear children. Here, same thing, and let's focus on this point. This is the point is moving in this direction. Same way. So mechanical energy is able to rotate this coil. So thumb is pointing the motion of the conductor and the forefinger is pointing the magnetic field lines, and you see my middle finger direction in the direction of induced current. By using the same Fleming's right hand rule, here also you can use to find the induced current direction. And induced current direction is same here, but interestingly, now the induced current is reaching to slip ring 2. Slip ring 2 is connected to carbon brush 2. So now like this it is moving, and you can see C1. C1 is having connection to S1. S1 is having connection to the shorter lead, and it goes like that. Okay, clear? If you are not understanding, go back to your 10th standard. 10th standard, the same things are there. Actually, in 12th standard, it is not at all required to discuss with this much detail. Right? If you are not understanding this, just go back to your 10th standard and refer AC generator, which is a very, very important long answer, which was a very important long answer type question then. Right? Now, alright, so now the current is moving from C2 to C1, and previously the current was moving from C1 to C2. Okay, so current is moving from C2 means it is behaving as a positive terminal. Alright, C2 is behaving as a positive terminal, C1 is behaving as a negative terminal, and previously C1 is positive, C2 is negative. Now C2 is positive, C1 is negative. Alright, clear? So this is what, for every half rotation, you see the direction of current is changing. The direction of current is changing for every half rotation. That's what I am writing here. The direction of current is changing for every half rotation, my dear student, and that's called the alternating current. The current is alternating, means changing its direction for every half rotation. Okay, and in the coil, current direction is changing. See, in first case, current is moving from A, B, C, D in the coil. Here, in second half, current is moving from D, C, B, A. In the coil, it is changing. In the coil, it is changing, and in the circuit, in the whole circuit also it is changing. In the circuit, in first half, the current is moving from C1 to C2. In the second half, current is moving from C2 to C1. Okay, clear? The polarities of the batteries is changing after every half rotation. This is not the actual battery, it's called the virtual battery. As long as this phenomenon of magnetic flux change is linked with the coils, there is an induced EMF is produced. That induced EMF, how much we will be discussing right now. Before that, as long as this process is taking place, for one half rotation, this will be negative, this is positive. For the another half rotation, immediate half rotation, this will be negative and this will be positive. The polarities are keep on changing, my dear students. So that's called alternating current. Okay. Now, look at this interesting thing now. We know magnetic flux is equal to NBA cos theta. What is N? Number of turns of the coil. B, magnetic field. It's a constant magnetic field. A, area vector or area of the coil. Theta. Theta is the angle between B and A. And one more thing. So this is the theta is equal to omega into T. What is omega here? So angular velocity. That's omega. In the last class I told you. So from here, this one I can write phi is equal to NBA cos omega t. I can write like this. Okay. And we know induced EMF is equal to minus d phi by dt. Okay. So this I can write minus d by dt of NBA cos omega t. So this I can write it as minus NBA into d by dt of cos omega t. D by dt of cos omega t. It's in the form of d by dt of cos theta. D by dt of cos theta is sine minus sine theta. Okay. So this is equal to minus NBA into d by dt of cos omega t will be minus sine omega t into omega. So minus minus cancel here. So the final answer I am writing here, look at it carefully. NBA omega sine omega t. Right? This is in the form of E is equal to E naught sine omega t. So what is this E naught? E naught is equal to, from here, E naught is equal to NBA omega. This is E naught. Right? You know what is this? It's called the maximum EMF. What is it called? Maximum EMF. Right? Maximum EMF produced in a coil. So that's what NBA omega. And this can also be written as E naught is equal to NBA omega can be written as 2 pi into frequency. F is frequency of the coil. Now here one more thing, if you divide this with R, you get EMF by R, that means voltage by R is the current, right? Voltage by resistance is current. This I can write I is equal to I naught sine omega t. So this is the current, EMF current, both expressions we have got. So where here I naught is maximum value of current. In the last line we had already discussed, I naught is the maximum value of the current. Okay, now let's draw the graph for alternating current. It's simple. This is EMF and this is time. So this is the graph indicating that this is first half rotation and the second half rotation. So first half rotation of the coil, there is a maximum EMF, and the second half rotation there is a maximum EMF in the opposite direction. Right? This is called positive half cycle. This is a negative half cycle of alternating current. This is where initially theta is 0 degrees. Right? What does it mean? Theta is 90 degrees. Initially theta is 90 degrees. Angle between B and A, theta must be 90 degrees. Well, then you get this graph. Okay. 90 degrees means what? So this is how the coil and the magnetic field lines are like this. So area of the coil is like this and the magnetic field lines are like this. For example, you can keep the coil in this direction. Right? Coil. Now, area of the coil, area vector of the coil is this one. The magnetic field lines are also in the same direction. Okay, again I am telling you, my dear students, and this is the coil location now. This is the coil orientation now. Maximum flux is linked with the coil. So this is the magnetic field lines and this is only the area vector. If the theta is 0, maximum flux is linked initially. Okay, in that case, when the initial position of the coil is here, this is your alternating current direction. This is your alternating current form. If the initial orientation of the coil is like this, so you get the alternating current in this way. It's E and it is T like this. No confusions. So this is your E naught and this is your minus E naught, and this is the graph is E is equal to E naught sine omega t, and this is the graph, this is a sine function graph. Okay, so now this graph is E is equal to E naught cos omega t, my dear children. Clear? So this is how the concept of AC generator is also discussed, right? So if there are one or two simple or some more topics, some additional topics are also available in this chapter. Not only in this chapter, whatever we have discussed the chapters so far, there are some important and additional topics, right? So those things will be discussed in our offline classes, which we are expecting to start as early as possible. All right, and this is what the chapter called Electromagnetic Induction. All the very best for your today's assignment and in this week's exam even.